Hello everyone, welcome to the 7th video in the series of graph theory. This video will cover about Eulerian and Hamiltonian graph. We will recollect that in our last video we saw about path, circuits and connectivity. Path is nothing but an alternating sequences of vertices and edges, starting with an vertex, ending with an vertex. If you have alternatively a vertex and edge and so on, then you call that to be a path. And if the edges are going to be distinct, you will call it as a simple path. If the starting point and the ending point of the path is going to be one and the same, then you call it as a circuit or you call it as a cycle. And if that also has exactly the edges in only once to be appearing, then you call it as a simple path or a simple cycle. And the length of a path or a cycle is going to be the number of edges that appears over that. Now in this video we will see about Eulerian paths, Eulerian circuits, Hamiltonian paths and Hamiltonian circuits, which will otherwise be referred to as Eulerian graphs and Hamiltonian graphs. Come on, let's get started with the definition of what is meant by an Eulerian path. If every edge, what we have to be very careful over here is the word or the important quantity which is going to be edge. If the edge of a graph is included exactly once, so every edge of the graph is included exactly once, then what do you call that path as? It is an Eulerian path. Notice, a path need not have to cover all the vertices and all the edges. But when it comes to Eulerian, the point is that every edge must be included from the graph G exactly once. So you can remember in this way, E is going to be Eulerian. What do we need to include? We need to include edges. So E for E. So every edge of the graph G is being included once exactly. Then you call the graph as an Eulerian path. Okay. So now we can see from the given diagram, I start with B. I move with my A and I cover this edge. I move with E and I cover with this edge. I move with this back to B, I cover this edge. I move to C, I cover this edge. And I move to D and I cover this edge. So all the edges are being covered, and how many times? Exactly once. So such a path where you start from B, A, E, B, A, E, C and D. This will be called as an Eulerian path as it covers all the edges exactly once. Now, what is meant by a Eulerian circuit? A circuit of G is called as an Eulerian circuit if it includes each edge of G exactly once. So, it has to be a circuit. What do you mean by a circuit? It starts at a point and it ends at the same point. Okay. So you start and end at the same point. Then what do you call this as? You call this as a circuit. You go from A to B to C to D and back to A. Notice when we write a circuit, you will have to write it as A, B, C, D, A. You will have to begin with A. You will have to end with A. So the starting and the ending point have to be one and the same, in which case you call it to be a circuit. If you are stopping with D, A, B, C, D, it just becomes a path because the ending point is not as the same as your starting point, in which case you refer this as a path and not as a circuit. So for a circuit, the beginning and the ending point have to be one and the same. And now if a graph contains an Eulerian circuit, then you call it by the name Eulerian graph. Now look into the example given below. You start with A, you go to B, you go to D, you go to C, you go to B back, E back and then to A. So you go A, B, D, C, B, E and then back to A. You cover all the edges exactly once, and so you call this to be an Eulerian circuit. And this graph that contains the Eulerian circuit will be referred by the name called as Eulerian graph. Now, the theorem which we have says a connected graph contains an Eulerian path if and only if it has exactly two vertices of odd degree. So, if and only if, meaning it is a necessary and sufficient condition. So, if it is an Eulerian path, it has exactly two vertices of odd degree, and if the graph has exactly two vertices of odd degree, then it will be an Eulerian path. Now, we see that 1, 2, 3. The degree of my vertex B is going to be 3, and one more vertex of odd degree is going to be D. Over here the degree is 1. So you have exactly two vertices of odd degree, and you are able to find a path that is going to go or reach all the edges exactly 1. B to A, A to E, E to B, C to B to C, and to D. So we are able to find a path if there are going to be exactly two vertices, an Euler path, and if there are going to be an Euler path, then you have exactly two vertices that is going to be of odd degree. Now moving on to the next concept called as Hamiltonian, next theorem, which says a connected graph contains an Eulerian circuit. The first one which we saw over here is for path. And now for your circuit. How about a circuit if and only if each of its vertex is of even degree? So all your vertices must be of even degree. Only then we will be able to find a circuit, because a circuit has to start at a point and it has to reach back to the same point after traversing a series of sequences of vertices and edges. So you can have that only if the degree is going to be even in nature. If it is odd, you will get stuck over there and you will not be able to return back. So we say that it has a circuit if and only if all of it is going to have even degree. Now notice A has degree 2, D has degree 2, C has degree 2, D has degree 2, and B 1, 2, 3, 4. All the vertices over here are of even degree, and so I am able to find an Euler circuit. So I move from A to B and then to D, B to C, then to B, E, and then back to my A. I started with A and I ended with A. So a circuit is possible only if all of them are going to be of even degree. So this is going to be a necessary and sufficient condition, so using which we can say whether a given graph is going to have an Eulerian path or an Eulerian circuit or not. This theorem guarantees for Eulerian circuit and this theorem guarantees for Eulerian path. If there are exactly two vertices of odd degree, there is a path, and all the vertices are of even degree, then there is a circuit. Now coming to the next concept called as Hamiltonian path. A path of a graph G is called as an Hamiltonian path if it includes each of its vertex of G exactly once. So when Eulerian was concerned with your edges, now our Hamiltonian is one which is concerned with our vertices. So you keep it in mind. Hamiltonian means you will have to traverse your vertices. So if I am able to touch each of the vertex of G exactly once, then you call such a path to be an Hamiltonian path. Now you see that I start with A, I go to E, next I move to E, I then go to my B, and then from my B I go to my C, and from my C I go to my D. So I am moving from all my edges A, E, B, C, D. How many times? Exactly once. And have I left out any vertex? No, we have not. So keep in mind, what we are concerned is only vertex, don't bother about edges. So we may ignore edges. What we are concerned in a Hamiltonian path is all about vertex alone. So if I am able to touch all of these vertices exactly once, then I am able to find a path. So that path will be called as an Hamiltonian path. And now comes the Hamiltonian circuit. So you start at a vertex and you get back to the same vertex After completing all the vertices exactly, or after touching all the vertices exactly one, then you call it as an Hamiltonian circuit. So, except for the starting and the ending vertex, all the vertices that appear have to be distinct in nature. So, let me see where I go about in this graph. I start with A, I go to B, I next move to C, I next move to D, and next I move to E, and next back to A. Now see, I have covered the vertices of the graph G, all of them exactly once, and I have reached my starting point. I have started with A, I have ended with A, covering all the vertices exactly once. So what do we call this circuit as? This circuit is called as an Hamiltonian circuit. Now, if my graph contains an Hamiltonian circuit, then such a graph will be called as an Hamiltonian graph. Now, the difficulty over here is, for an Eulerian circuit or an Eulerian path, we have the necessary and sufficient condition for the existence of a path and the existence of a circuit. But there is no hard and core proof for the existence of an Hamiltonian path or an Hamiltonian circuit which is available. So we just take a point over here to notice what can be done best, which the first note says that if there is going to be an Hamiltonian circuit, there is for sure an Hamiltonian path. Ignoring just the last vertex, you can have the path. Now let me have A, B, C, D, and now I am going to move to E, A, B, C, D, E. So what has happened over here? I started with A, I go to B, I go to C, I go to D, I go to E. This is going to be a path. What type of path? It is going to be an Hamiltonian path. But does it have an Hamiltonian circuit? What do you mean by a circuit? You have to get back to the same starting point again. Is it possible over here? No. You cannot get back to the same point after touching all the vertices once. But let me consider this graph over here. A, B, C, D, E. I start over here. Now consider this graph. If I am going to start over here with my A, I go to B, I go to C, I go to D, I go to E, and I move to A. Now I am able to travel all my vertices exactly once and get back to my same starting point. This is going to be an Hamiltonian circuit. Does this have an Hamiltonian path? Yeah, you can very well form this as you traverse from A, go to B, go to C, go to D, and move to E and stop over here. So what do we do is just ignore or getting back to the starting point A itself. So when you ignore the starting point A, what you have in hand is going to be an Hamiltonian path. So the concept says if there is a circuit, for sure you will be having a path by just deleting the repeating or the starting vertex alone. But the converse is not to be true or need not be true. Here we had a path, but did we have a circuit? No, that was not possible for us to make. So keep in mind, if there is a circuit, just ignore the last one and then form the path. But if you have a path, it is not necessary a circuit will always exist. The second point says a complete graph Kn with n having greater than or equal to 3 vertices will always have an Hamiltonian circuit. What do you mean by complete graph? A complete graph is one where every vertex is connected to every other vertex by means of an edge. So if we are going to have 3 vertices, 1, 2 And 3, every vertex is connected to every other vertex by means of an edge. So we are able to find a Hamiltonian circuit which starts over here and ends over here. When we are having it as 4 vertices, what is going to be this K4? Every vertex is attached to every other vertex by means of an edge. So obviously we will be able to find one. What is going to be your K5? Your K5 is one where you can traverse everywhere over here, and with every other vertex you join these one. So this is going to be your K5. When you are just roaming around your boundary of your K, then you will be getting your Hamiltonian circuit, which makes sure that you start at the vertex and you end at the same vertex. So these are some clues by which I will be able to find whether the Hamiltonian circuit or a path exists, but there is no going to be hard and foolproof that for sure there is a path or for sure there is a circuit like what we had for an Eulerian concept. Now let us give some examples of graphs which are going to be Eulerian but not Hamiltonian. So come on, what do you mean by Eulerian? Every edge have to be traveled exactly once. So we will start with B, we go to A, we cover this, we go to E, we cover this, we go to B, we cover this, we go to C, we cover this, we go to D, we cover this, and then it is going to be back to B. So we have covered this. So all the edges have been covered exactly once. So this is going to be an Eulerian graph as it contains an Eulerian circuit. But how about Hamiltonian? What do you mean by Hamiltonian? Every vertex must be covered exactly once. Notice that when we are traversing, the vertex which is B is going to appear twice. Whatever means you try to travel, you cannot ignore this point B and then travel. So does it mean that we can cross the graph without moving to B twice? No, that's not possible. And hence this graph doesn't contain an Hamiltonian circuit, and so you cannot call this graph to be an Hamiltonian graph. So this is an example of a graph which is Eulerian but is not Hamiltonian. Next one, what we want is an Hamiltonian but not Eulerian. What do you mean by Hamiltonian? Every vertex must be covered exactly once. Let me start with A, let me move to B, let me go to C, let me go to D, E, and I am back to A. Now all the vertices are covered exactly once. So this is going to be Hamiltonian in nature. So it is an Hamiltonian graph. But is it Eulerian? E for edges. Does it cover all the edges? No. We notice that this edge hasn't been traversed, this edge hasn't been traversed, which ignores these edges, and hence you cannot call this graph to be an Eulerian graph. Next, what we need is both Hamiltonian and Eulerian. Yeah, you can start with A, go to B, go to C, go to D, and back to A. Now all the 4 vertices have been touched for. And as you go from A to B, you are covering this edge. As you go from B to C, you are covering this edge. From C to D, you are covering this edge. And from D to A, you are covering this edge. Which means all the edges of the graph is also covered. Hence, it becomes Eulerian in nature. But we notice that this is going to have the same circuit for both Hamiltonian and Eulerian. Say suppose they are asking you for one which is going to be a different one, an Eulerian circuit which is different from that of an Hamiltonian circuit. Then how can you construct that? Just mark an extra amount of 2 edges between any 2 points or vertices over here. So as I move from A to B to D to C to A, I will be covering all my vertices exactly once. So it makes it as Hamiltonian. And when I go from A to B, B to D, D to C, C to B, B to C and back to A. I cover AB, I cover BD, I cover DC, I cover C to B, I cover a B to C and then back to my A. I start with A and end with my A, covering all the edges exactly once, and it is quite different from that of the one which we formed over here, and so you can call this to be Eulerian. So this graph is an example of a graph that is both Eulerian and Hamiltonian, but it has two distinct paths, two distinct circuits. But over here, both your Hamiltonian and the Eulerian circuits are going to be one and the same. To end with, we need an example of a graph that is neither Hamiltonian nor Eulerian. How to check if it is going to be Eulerian? If all the vertices are going to have even degree, then we can call it to be Eulerian. We notice that this vertex is going to have odd degree, so an Eulerian graph is not possible for this one. What do we mean by Hamiltonian? Hamiltonian means every vertex must be covered exactly once. But is it possible to reach your C without crossing the point B twice? No, that doesn't happen over here. So this means that this graph is not Hamiltonian in nature too. So this graph is neither Eulerian nor Hamiltonian, giving us the various combinations in which we can have graphs seen from example number 1 to example number 4. So I hope these examples would have helped you to understand the concept of Eulerian and Hamiltonian graphs to a greater extent. Happy learning. Keep learning. Thank you.